All right, so let's look at this y-intercept for a second. With this particular set of data, we got a y-intercept of negative 0.01371 centimeters. Okay. So stop and think about what this y-intercept is telling us. So our best fit line comes along and crosses the y-axis at this point. So at negative 0.01371 centimeters. That's where it crosses that y-axis. This is also the place where the value on the x-axis is 0. So what is our x variable? Our x variable was the diameter of a circle. So according to our graph, if we have a circle with a diameter of 0 centimeters, then the circumference of that circle should be negative 0.01371 centimeters. Does that make sense? If we have 0 diameter, we should have a 0 circumference. So something seems off. Our intercept is close to 0, but not quite. So can we ignore it? Can we just say, oh, that's close enough and go on with our day? Maybe. We're going to look at that just a little bit. So why would it not be 0? Well, measuring circles is hard. So the probability that some human error went on in there to kind of affect our data would make sense. And if we look at our data points, there's a pretty nice, straight, general trend. But if you look at our best fit line, those data points aren't exactly on that best fit line. So our data wasn't exactly accurate. So the question becomes then, is our data good enough to be able to use this to derive our relationship? Now all of that depends on our best fit line, right? What if this data point had been down here just a little bit? Our best fit line wouldn't have gone here, but would have been skewed a little bit this way. So what would have happened to our y-intercept? It would have been a little bit higher up on the x-axis. Same thing if this were a little bit higher. Instead of our best fit line being here, we would have maybe kicked it up, not quite that much, we kicked it up a little bit and our intercept would have been lower on the y-axis. So the question becomes then, is our data good enough to be able to use to derive a relationship? Now there's a lot of different ways that we can analyze our data. We're going to use a really pretty simple one specifically to analyze the y-intercept. And statistics people among us are probably going to have a fit over this. But this is just a quick way to kind of see if our data is accurate enough that we can say that this is in fact 0. And this is just called an intercept analysis. And it focuses specifically on the y-intercept and whether or not it's small enough to ignore it. So if you take the value that you have for your y-intercept, okay, in this case, negative 0.01371, so we're going to take the value of our y-intercept. I can't remember that number. 1371. And divide it by the highest y value that you measured. Now our y value was circumference, so if we come over here to our data table, the highest y value that I measured was 32.1 centimeters. So we're going to divide by the maximum y value that we have. Okay. Now this is actually the absolute value. It doesn't matter if it's positive or negative. It can be up this way or it can be down this way. So when we divide this, we are going to get 0.0004. Now if we multiply this by 100%, we have, move our decimal over, 0.04%. So what this tells us is this y-intercept is 0.04% away from where it should be. If this number is less than 5, either way, positive or negative, we can say that our y-intercept is negligible. We can ignore our y-intercept. So in this situation, since this is less than 5%, we can say our y-intercept doesn't matter. So we can come back and we can say we have 0 diameter, 0 circumference, our y-intercept is negligible. So we have good data. Now what if you can't ignore your y-intercept? You want to look at your data. What if we would have had a data point that was way, way down here? This doesn't fit with our general trend and it skews our relationship a little bit. This might be something you'd want to go back and remeasure. It might be something you want to throw out. Maybe this circle wasn't actually a circle. You want to go back and look at this particular data point to see if that's what the problem was. Now, the y-intercept can also be high if you were consistently doing something incorrectly. A common issue with this particular lab is measuring from the end of the ruler. Now, if you look at this ruler here, if you were to measure from the end of the ruler, you're not measuring from 0. There's a little bit of error there, maybe half a centimeter. So if you had a y-intercept of a positive half of a centimeter, that could be why. So you want to look at your measuring tools as well. Now, if you've done your calculation and the percent is less than 5, you can ignore the y-intercept, and it's just like it was measured to be 0. So in this case, we would leave it off of our equation as well. So now let's look at our slope. We already talked about how this is a direct relationship, and we have written an equation to describe this line. And we've even defined this line. If you go back and look at our annotations video, we have defined this line as pi. The important takeaway about the slope is that in physics, the slope of a graph between two specific variables often define a specific physical property. So slope is rise over run, right? So we've got 2 points. We're going to go rise and run. So this change here and this change here, how much does our slope change in between any 2 points? So in this case, our rise is circumference in centimeters, and our run is the diameter in centimeters. So in this example, dividing the circumference by the diameter gives us a slope of 3.061 centimeters per centimeter. Let's break this down a little bit. It's pretty easy to see that the diameter of a circle increases, then the circumference is going to increase as well. And since the best fit line is a straight one, we can say that the rate of change is constant. The value of the slope, in this case 3.061 centimeters per centimeter, tells us this rate of change. So the circumference of the circle increases 3.061 centimeters for every 1 centimeter that our diameter increases. This is true for every 1 centimeter change in diameter. So a circle with a diameter of 1 centimeter will have a circumference of 3.061 centimeters. If we increase the diameter to 2 centimeters, the circumference will be 6.122 centimeters. Now if we come back to this equation that we wrote, that I don't have on here, so this was our equation. Circumference was equal to our slope times the diameter. When we say equation, we mean a way to determine the circumference if we know the diameter. This is a mathematical equation. If we know that our diameter is 1 centimeter, we can plug that in, multiply it by 3.061, and find our circumference. If we know that our diameter is 2, we can take this times 2 and find our circumference. For a circle with a diameter of 3, we can plug that in for a diameter and find the circumference. We can go in reverse as well. Maybe we know the circumference and we want to know the diameter. So we can go backwards. Whichever variable we know, we can solve for the other one. So we mentioned in our annotations that we can use a graph to define some property. In this case, we're defining the constant pi. The slope of a line between the diameter and the circumference is pi. That's the property of the circle that this graph is defining. Now, we probably know that pi is a constant. And if you punch this in your calculator, you get 3.1415926 something. And it goes on forever, right? Typically, we just use 3.14. But look at our slope. We didn't get 3.14. We got 3.061. This is close, but not perfect. But we can figure out how close. This is called percent error. So how close were we to the actual answer? How accurate were we in our measurements? Think about a 10-point quiz. You get a 9 correct. Typically, we talk about the percent correct, or we got a 90%. But how much is that in error? So what was our percent error on our quiz? It's pretty easy to figure out that that was 10%, right? But how did you do that? You took the actual value that you got, and you subtracted the accepted value, and then you divided by the accepted value. And you got a percent from that. Okay. So in a percent error, just like we do on our tests, we can do that with any known quantity. So in this case, we're going to take our actual, which was 3.061. Let's leave that off because that cancels out. We're going to subtract 3.14, and we're going to divide by 3.14. Now notice we're going to get a negative percent. What does that mean? Well, it just means that we were below. Okay, we were under the accepted value. And if we calculate this out, we're going to get negative 0.025. And if we multiply that by 100%, we're going to get 2.5% error. So I was 2.5% below the accepted value. Not too bad. Really for this particular lab, since it's your first foray into measuring and it's circles, anything within about 10% is pretty good. So here we've got a couple ways that we kind of look at how good our data is. Are we taking accurate data? We can look at our y-intercept, and we can look at that percent error.